Have you ever just looked at the stuff around you? I mean, really looked. Your chair, your coffee mug, the device you're watching this on right now, every single one of them started out as just raw material. And today, we're going to pull back the curtain on the incredible processes that shape our entire world. It kind of feels like magic, right? You take a formless blob of something and turn it into a precise, useful object. Well, it's not magic, it's engineering. And it all boils down to one single fundamental idea. So let's get right into it. To really get how we make almost anything, whether it's a massive steel beam or a tiny plastic gear, we first have to understand what happens when you push a material right past its breaking point. This right here, this is the big secret. Think about a paper clip. You can bend it just a little bit and it'll spring right back. That's called elastic deformation. But if you bend it far enough, it stays bent. That's it. You've just caused plastic deformation. You pushed it past its yield strength, and now its shape is permanently changed. This is the absolute core of how we form metal. Right, so once a material hits that point of no return, that plastic deformation, its internal structure is changed forever. But how engineers control that change is where things get really fascinating, and it all hinges on one critical variable. Yep, just that, temperature. Whether you apply all that force when a material is scorching hot or when it's cold completely changes everything. It alters its properties in huge, dramatic ways. This one choice is a massive fork in the road for making just about anything. And this brings us to the central theme here, this constant battle between hot working and cold working. Now, to understand this divide, we first need to get our heads around a very specific temperature. Okay, this sounds technical, but stick with me. This is not the melting point. Think of it more like a healing temperature. When you bend and deform a metal, you're creating all these tiny defects and stresses inside its structure. But if you heat it up past this recrystallization temperature, the metal can literally grow brand new perfect grains. It's like wiping the slate clean. So check this out, because this is where you see the trade-offs in action. When you work a metal hot, above that healing temperature, the metal is constantly fixing itself. You don't build up stress, and it's way easier to shape. But working it cold is the exact opposite. You're deliberately building up all those stresses and defects. All these microscopic imperfections get tangled up, making it way harder for the material's internal layers to slip past each other. We call that work hardening, and it's how you make a material stronger, but also more brittle and more likely to crack. All right, so we've got the theory down, hot versus cold. But what does this actually look like in a factory? How do you make an I-beam or a car door using these principles? Let's take a quick tour of the real-world techniques. Rolling is one of the most common processes out there. You basically take a huge slab of metal and squeeze it between these massive rollers to make it thinner and longer. Honestly, it's just like rolling out pizza dough, but on a much, much bigger scale. And of course, whether you do it hot or cold makes all the difference. And this is the perfect example of that trade-off we were talking about. Hot rolling? That gives you metal that's tough and ductile, really easy to form into something like a structural I-beam for a skyscraper. But cold rolling, that gives you a stronger part with a much smoother, more precise surface. Exactly what you'd want for the body panels of a car. Okay, rolling is great for flat stuff. But what if you need something complicated? With complex curves and hollow parts, like an engine block. You can't just bend a sheet of metal into that shape. You need a totally different approach. You gotta go liquid. And that's where casting comes in. The idea couldn't be simpler, really. You melt the metal, you pour the liquid into a mold, and you let it cool down. Sometimes that mold is a one-and-done deal, like a sand mold you just break open to get the part out. Other times, it's a super durable metal mold that you can use over and over again for mass production. But wait, there's a third way, and this one is kind of wild. It's not quite forming a solid, and it's not casting a liquid. It's called sintering. With this, you take a material in powder form, press it into the shape you want, and then heat it up. But, and this is the key part, you don't actually melt it. The little particles just get hot enough to fuse together into one solid piece. So why would you do this? Well, sintering is amazing for creating super dense, super strong parts from materials that are just a huge pain to melt, like high-tech ceramics or exotic metals. By squeezing all the empty space out from between the powder particles, you massively improve the material's properties. So, we've talked a lot about metal, whether it's solid, liquid, or powder. And it turns out those exact same ideas, heat, pressure, and molds, are absolutely essential for that other material that pretty much runs our modern world, plastic. When it comes to plastics, injection molding is the undisputed king. It's all about speed. You take these tiny plastic pellets, melt them down, shoot that molten plastic into a super precise mold under intense pressure, let it cool for a few seconds, and bam! A finished part just pops out ready to go. The whole cycle can be over in seconds. But of course, not all plastics are created equal. An engineer has to pick the right tool for the job. You need something with glass-like clarity, maybe for a car's taillight. You're going to go with acrylic. Need something super strong that can take a real beating? That's ABS. It's literally what Lego bricks are made of. And for your phone case, you'd probably want polycarbonate because it's unbelievably tough and stays that way whether it's hot or cold. So when you put it all together, you realize that every single object we use is the end result of a long chain of very smart, very deliberate decisions. It's a complex balancing act that engineers have to navigate for every single thing they design. And this is the big takeaway right here. There is no single best manufacturing process. It's always a game of trade-offs. Do you need the brute strength of a cold-worked part or the flexibility of a hot-worked one? Do you need a perfect glossy surface finish, or do you just need to make a million of them as cheaply and quickly as possible? These are the questions that define the modern world. So, do this for me. Look around you right now. Pick up your keys, your phone case, that water bottle on your desk. They're not just objects anymore, are they? They're telling a story of heat and pressure and 1,000 tiny choices. And the really cool part is, now you know how to read it.